All right, everybody, let's get the lecture going for, well, I was going to say this afternoon, but I mean, it's a bit kind of too early. I know, like, technically it is afternoon, but it's not really the afternoon, is it? It's afternoon, doesn't start a bit later. Is anybody else cold? It's freezing in here. Is it just me? Or is it, it's not just me, right? It is cold in here. Okay, so hopefully it's going to warm up eventually. But if it's a bit chillier, I don't know, maybe that helps to focus. So I hope everybody is really excited for the lecture today, because we are really kicking things off and getting into some fantastic physics. And the subject for today is we're going to be focusing on forces, and we're going to be specifically thinking about forces as a kind of vector. We've just covered vectors in the last lecture, and we approached vectors in a general way. So we weren't thinking about a specific kind of vector. It didn't have to be, say, the magnetic field or something like that. We were just thinking about general principles which apply to any kind of vector. And today we're going to be applying some of what we did last time specifically to forces. So we've got some really beautiful geometric principles coming up. So I hope you guys are really going to enjoy this one. Now, some weeks it takes a bit of sort of creative thinking to find a really good image which kind of sums up everything we're going to be doing in the lecture and has a really good connection. But this week, I thought there was really only one image we could use to start with, because of course, if we're thinking about the force and we want to learn about forces, well then you've got to go to the planet Dagobah, of course. You may have noticed by now that Empire Strikes Back, it's one of my favorite movies. I think this is all we've got on it for now. So of course, you know, when Luke Skywalker wants to learn about the force, he goes to Dagobah and he learns about, you know, the force in Star Wars, the kind of the mystical force. And he's being trained here, of course, by Jedi Master Yoda. But I thought there were some interesting things going on in this picture, specifically over here. So we've got Luke and he's balancing upside down and doing a handstand, and he's got Yoda balanced on one foot. And from the looks of things, applying the eye of a physicist, to me, it doesn't look like they're relying on the force, you know, the mystical Star Wars force, to achieve this rather impressive feat of balance. To me, it looks like he's just doing a really good one-handed handstand, and he's balancing Yoda on one leg, and he has the other leg, you know, out over there to keep him all balanced, and he's got his hand out. So it looks like to me that he's in what we would say physical equilibrium, a static equilibrium. So all of the forces, all of the turning forces on Luke and Yoda are in equilibrium, and that's what's keeping him nice and stable there. So it doesn't look like he's relying on channeling, you know, the Jedi force to make any of this happen. And it's all of these things which we're going to be learning about today. So we're going to start by thinking about forces as a kind of vector. So those principles that we learned about last time, especially vector magnitudes, this is a very important one for forces. We're going to be seeing how they apply to forces and how they affect our physical objects. We're going to be looking at two different types of what we say equilibrium. So equilibrium is just whenever anything is balanced, and there are these two main cases. So as we see in this picture here, it looks like everything's balanced, everything's static. We say that's static equilibrium. A slightly more counterintuitive kind of equilibrium is what we call dynamic equilibrium. And this might be a bit counterintuitive, because if we think about things moving, you might say, well, that's not really in equilibrium, is it, if things are moving around all the time? So we're going to see how we can keep something in equilibrium even if things are static. And we're going to look at stability and a couple of the conditions for equilibrium. So a couple of the things that we need for things to remain in equilibrium. All right, so that's the plan for today. So let's start by having a quick kind of warm-up question, get the brain working a bit. Let's see what this question is over here. So let's try this warm-up question. Let's see what we have for the units of force. So remember this convention here, that if we have some quantity and we put it in square braces, that means we're thinking about what the units of the thing are. Let's see how we're doing. Okay, let's take a look. Let's see what we get for the units of force. Let's have a look. Okay, looks like most people are going for B. Okay, so very well done. That's the correct option. Okay, so it's newtons are the units of force. If you remember last week, we were talking about we had derived units and base units. So newtons are a derived unit. They're not a base unit. And over the next couple of weeks, we're going to be thinking a bit more about what goes into making a newton as a unit. But for today, we're just going to be thinking about, okay, newtons, that's the units for force. So very well done, everybody who got that one correct here. The correct answer is newtons. Now, this question is a bit more interesting because whenever we're discussing forces, you're going to hear people talking about what we call net force. And this is a really important concept when we're thinking about the effect that forces have on things, the net force. So what do you think we mean when we're talking about the net force acting on something? So have a look at those options and see what you think. Okay, let's take a look at the responses. Let's see what everybody thinks here. Okay, oh, very good. Okay, so most people are going for D. Okay, and that's of course the correct answer. So when we're talking about the net force, we just mean it's the resultant of all the forces acting on an object. So we had that example on Monday when we calculated the magnitude of the resultant of a couple of displacement vectors. So very often if we're combining displacement vectors, we want to know what the resultant is, and it's especially important when it comes to forces. We want to know what the net force acting on something is, because that's what's going to affect the dynamics of the whatever we're considering, really. So very well done, everybody who gave that one a go. Let's try another question now. So what this question is about, if we just have a stationary object, so maybe let's think about we got this box of chalk here, and it's just sitting there perfectly stationary, minding its own business. What can we say about the forces acting on this object if it's just sitting there stationary? All right, shall we have a look? So we've got a range of options here. Let's take a look. What does everybody think? What's going on if an object is stationary? So some people, we've actually kind of covered all the bases here. Now, I can see why people might be going for option A, because, you know, if we just have a stationary box of chalk and you say it's stationary, you might say, well, it's only going to be stationary if there's no forces acting on something at all. And that certainly is one way that something can be stationary. Maybe there are no forces. So I can see why people might be going for that one. But a slightly more kind of general thing is maybe there's no forces on it, or maybe what we say the net force acting on it is zero. Because if the net force acting on something is zero, then all the forces are balanced and it's not going to be going anywhere. So the correct answer is that the net force has to be zero. So very well done, everybody who got that one there, okay? So sometimes maybe we just have one force acting on something, maybe we have multiple forces. But there's a really interesting phenomenon that happens when something is in what we call equilibrium. There's a really interesting thing we can say about the forces acting on it. So suppose the net force on something is zero. What can we say about the individual force vectors acting on the objects? While people are thinking, I might draw a little sketch here. So suppose maybe we've got we've got an aeroplane. Aeroplanes are kind of difficult to draw, so we've got the tail and we got the wings over there. So if we've got an aeroplane, then maybe there's going to be some force of gravity acting on the aeroplane, and there's going to be some force of lift from the wings, and there's going to be some thrust from the engines, and if the plane's just flying along there, then there's going to be some drag as well. So maybe think about what all those forces are going to look like. What could we say about those forces if the object is stable? Let's have a look how we're doing here. Okay, let's take a look. So if the net force on an object is 0, what do we reckon here? What are the options? Oh, okay. Okay, so we've got kind of range of options here. Now I can see why people might be going for the equilateral triangle one. Triangles, they're always nice and balanced, nice and symmetric. And in fact, if we did have 3 forces acting on something which had equal magnitude and there was no net force, then the forces would in fact combine to form an equilateral triangle. So I think if people went for that, I think that's kind of good thinking. I like your thinking there. But we can always have more than 3 forces acting on an object, and it makes things a bit more interesting. Now, sometimes maybe all of the forces are going to be orthogonal, so as you say, perpendicular to each other. So in this example here, I guess all the forces, they are perpendicular to each other, but they don't necessarily all have to be perpendicular to each other. So these ones are kind of interesting because they can be true in some situations, but they're not the most general. The most general situation is that all of the forces will actually combine to form a closed polygon. So that's option A. So very well done, everybody who got that one, because that's quite a tricky one. We're really trying to generalize there. Personally, I think this is a really beautiful geometrical feature that we get when we're thinking about forces of something in equilibrium. So very well done, everybody who got that one. Now, this is a bit of a tricky concept. So I thought what I'd do, maybe put up a couple of slides and just kind of demonstrate what's going on with this. So suppose we've got a kind of classic physics example. We've got some mass and it's just suspended from a chain. So it's not doing anything particularly exciting. It's just sitting there. So maybe this mass could be a car engine or something like that. It's just sitting there and the force of gravity is acting on it. If we know, well, since we know that the mass is just sitting there, we know that the net force has to be 0, and that's coming from the tension in the chain. So gravity is pulling the mass down, and the tension in the chain is keeping the mass where it is. So it's nice and balanced, and the mass is just sitting there. And you might notice that those 2 forces have the same magnitude. We can make this a bit more interesting if we also pull the mass from a different direction. So suppose we came in here and we pulled the mass, we attached it to the side of the wall there. So now we have 2 chains, 2 forces pulling the mass in 2 different directions. The mass is still being affected by the force of gravity, so it's still being pulled down, and that hasn't changed. The mass it's not got heavier or lighter, gravity hasn't changed, so that force is the same. But now we have 2 forces acting on it. So this second chain, it's going to be pulling the mass sideways like this. Now we know that if the mass is stationary, the net force has to be 0. So we know that the tension in the chain has to be coming from something like this. So that tension in the first chain has to be going off at an angle. If we just look at these 3 forces by eye, It's kind of tricky to see if there's anything particularly special going on with them. We just have three forces. I mean, a couple of them are at right angles, the other one's going off at an angle. It would be difficult to kind of draw too much from that. So what I'd like to do is show you what we get if we just move the forces around a little bit. So I'm going to move the forces around, but I'm not going to change their magnitude or change their direction. I'm just going to slide them around, just a bit of a rearrangement, and see what we get. Let's see what we get when we move the forces around. So if we bring this force down here, and then that tension force down there, you see that the forces form a closed triangle like this. I think this is a really beautiful geometric result. So in the case that we have three forces of something at rest, it's going to form a closed triangle. And then maybe if we have this aeroplane here, we have four forces, that's going to form a square. So very well done everybody on that question who got that it's going to form a closed polygon, because that's quite a tricky one. Does anybody have any questions about this? I think it's a really nice geometrical principle. So in this example, this is what we would call static equilibrium. So the mass isn't moving at all, it's just sitting there. But there's also other ways that we can have what we say equilibrium. So let's have a think about this. So in this question here, suppose the net force acting on something is 0. What can we say about the behavior of something if the net force acting on it is 0? Let's take a look at the responses here. Let's see what we've got. Okay, so some people are going for B and C. Some people are going for A, but most people are going for D. So again, I can see why people might be going for option A. You know, if the net force of something is 0, well, then, you know, maybe it is just sitting there with no velocity. That's certainly an option there. Things can get tricky if we're thinking about behavior in a vacuum. That can be a bit counterintuitive. But the correct option is actually answer D. So if the net force on something is 0, it might be at rest, or it might also be moving with constant velocity. So correct answer is D. So very well done everybody who got that one. It's a bit of a generalization there. Does anybody have any questions about that, about net forces and resultant forces and stability before we move on? So in all of these situations, we're thinking about, is something just sitting there or is something moving around? But there's another important way to think about if something is going to be in equilibrium or not. And that's this question of stability. So I've got this picture here of an old-timey bus. And what they're doing is they're testing the bus for how far can we tip the bus over before the bus kind of tips all the way over and it's a really bad accident. And to us, it looks like this bus has been tipped over pretty far. And it looks like, well, I wouldn't want to be on this bus. It looks like it's about to fall over. But the bus is actually stable and it's not tipping over. So what I'd like to think about is, why is it that the bus is stable and not tipping over, even though to us it looks like it's about to fall over? So we've got this question here. So if an object is stable, what can we say about the center of gravity of the object? Okay, let's take a look at the responses. I'm curious to see what everybody thinks for this one. How's this object going to be stable? Okay, so again, we've got a pretty good range of options here. Not so many people going for C, but actually, so most people are going for option A. Okay, now this is an interesting one. So because we have two different things going on here. So when we're talking about the center of mass, we're talking about the weighted average center of where your mass is located. And then the geometric center, what we mean by that is trying to describe this without saying the geometric center. It's kind of halfway between all of the extreme points on the object. So especially if you're maybe an engineer and you're designing a car, you want to keep the center of mass as low as possible. So you want to put the engine or maybe the batteries or that kind of stuff as low as you can. So I can see why people might be going for A. But remember, if we do have a car, maybe we're thinking about a car, very often we're going to have that the center of mass of the car is lower than the geometric center of the car, because you want to put all of the heavy stuff as low down as possible. And then the kind of the cabin and the bit where people sit, that's not particularly heavy. It's not going to weigh too much. So if we want something to be stable, what we actually want to have is that our center of mass is over what we call the base of support of the object. So that's option D. So very well done, people who got option D there, because again, it's a bit of a tricky one. So we have a couple of pieces of jargon there. We've got the center of mass and the geometric center and the base of support. So I thought maybe let's just take one slide to have a look at all of these things in practice. So let's suppose we've just got a block here. So this block, it could be maybe a double-decker bus, or it could just be a breeze block. It's just something, and it's got some force of gravity there. So it's sitting there being nice and stable. So what's going to happen if we tip the block over just by a little bit? So in this block, the center of mass is actually equal to the geometric center of the block. So maybe it's just a solid block of concrete or something like that. Now we've tipped over the block there. What's going to happen? We need to look at where the base of support of the block is. So if we look at this corner here, we can see that the center of mass, it's still within the base of the block there. So if we tipped this a little bit and then let go, what's going to happen? Exactly, the block's going to tip back. It's going to go back to its original position. What if we tip the block just a little bit further? So tip it over this way. Now, you can probably start to notice things are looking a bit more dramatic. If we draw this little line here, have a look at where our base of support is. We've now moved the center of gravity just over the base of support. So if we tipped our block over this much and then let go, it's not going to go back to where it was. It's going to tip over all the way. And if this was a bus or something, clearly that would be bad news. You wouldn't want to be on that bus. That's the situation with something like a concrete block or something. Does this help us with that original picture that we saw of the double-decker bus being tipped over? Does that help us to understand what's going on there? Well, let's take a look at the situation. So we've got the bus here, and we need to compare where its geometric center is to where its center of mass is. So the base of support of the bus, that's just over the wheels there. So I've drawn that line just on the corner of one of the wheels. Let's take a look at where the geometric center is. So we can just look at that point there. And the geometric center is over, it's outside the base of support of the bus. And this is why, to everybody who sees this photo, you think, oh wow, that looks like the bus is going to tip over. I sure wouldn't want to be on that bus. So why doesn't the bus tip over? Does anybody have any thoughts? Yeah.
It's anchored down.
So that's a good thought. So you might think it's anchored down. So the bus, it's not actually anchored down. It's just sitting on a platform and they just tip it over. So why hasn't it tipped over? Any other thoughts? Yeah.
The engine is towards the bottom.
Great point. Did everybody hear that? So the answer is because the engine is towards the base of the bus here. So if you look, that's where we got all the engine and all that stuff. And the upper deck, that's really not going to be particularly heavy, especially when there's no passengers on it. So the center of mass of the bus, it's going to be somewhere over there where the engine is, because that's the real heavy, real dense thing on the bus. And we can see that the center of mass, it's still within the base of support of the bus. So it's a bit of an optical illusion. Even though it looks like the bus is going to tip over, it's actually quite stable. So we don't need to anchor the bus down to a platform to tip it over. Okay, so whenever we're thinking about things tipping over or exerting rotations on things, it's very helpful to think about what we call in physics turning forces. The forces that we've already seen, they're not turning anything, they're always maybe pushing or pulling something. So it's very useful to consider what happens if we're exerting forces which are turning something. Let's think about this example here. So maybe I've got a nut wheeled around a bolt or something like that, and we're trying to turn the nut, maybe we're trying to secure something down here. So you bring in a wrench and you're going to turn the nut, maybe you want to secure something up, you want to tighten something up. So we do this by exerting a force on the wrench. So you're pushing down at some point and you're turning the nut. You're essentially using the wrench as a lever. How much you're going to turn the nut depends on the distance from where you exert the force to the center of the nut. So if you've got this distance d, we can actually write down what the turning force on this nut is. So we're going to be exerting this turning force, and we can calculate what this is by looking at the product of that force and the distance, so how far it is from the center. So that's going to be our turning force. The nice way about writing turning forces like this is because it allows us to combine different turning forces which are acting on the same thing. So if we've got this wrench and maybe you're exerting the force, a certain force at one position, we can think what's going to happen if we come in and exert a different force at a different location. So maybe we've got this force over here, and maybe the force isn't as much, but we're exerting it at a greater distance from that center of rotation there. So we're going to get a different turning moment. And we can calculate what the total turning moment of something is just by adding together what the turning forces are. So we've got another question to think about here, because previously we were looking at the equilibrium of things when we think about them kind of moving around, but we can also think about the equilibrium of things when they're rotating. So let's have a think about this one. Let me just start this question up here. So if the net turning force on something is 0, what can we say about the rotational motion of the object? Got a few different options there. What can we say about the rotational motion? Okay, let's take a look at the responses here. I'm always curious to see what people think about this one. Okay, so nobody's going for A, few people going for B and C, and most people going for D. Now again, this is a bit of a theme for this lecture, because I can see why people might be going for B and I can see why people might be going for C, because if the net turning force on something is 0, well, maybe it is at rest. That's perfectly well. Something might be at rest if there's no turning force. That's fine. Equivalently, if something's turning at a constant rate, so maybe you're on a merry-go-round and it's just turning at a constant rate, you don't want to be spinning it around faster and faster and flinging all the children on the merry-go-round off, then maybe it's also rotating at a constant rate. So if something's rotating at a constant rate, the net turning force is also going to be 0. So what we see, in fact, is that there are these two different ways that we can have something with the net turning force being 0. So what we end up with is the correct answer is option D. So very well done to everybody who got option D. The last thing I'd like to think about for now is another example of combining turning moments in a really classic physics example. It's a very fundamental physics example, very important for understanding these principles here. Let's suppose we've got essentially a seesaw here, so maybe a balance, we're using it to weigh things. And on one side of the balance, we have a weight, and that weight is giving us 2 newtons of force on the balance. And that weight, it's 40 centimeters from the center of the balance. Then over on the other side, we have some mystery weight here. And that mystery weight, it's 30 centimeters from the side of the balance. We know when we have these 2 weights that our seesaw is nice and balanced. My question for you guys is, what is our mystery weight W2? Just remember that turning force, it's force multiplied by distance, and we know that they're both equal in this seesaw here. Okay, let's take a look at the responses here. Okay, so it looks like most people are going for D. So when we do the calculation, so when we work out the turning force on that one side, we set it equal to the other side, then we just divide by the distance, and we get that the W2, it's 2.7 newtons. So very well done, everybody who gave that one a go, especially if you worked out the correct value there. If you're not sure about this one, remember it's very handy to draw your own diagram of the situation. So maybe you want to draw a bit of a sketch like this, label the distances going on here. So we've got the 2 newtons, and then we've got mystery weight there, and we're trying to figure out what's going on. So if our mystery weight is equal to 2.7 newtons, then the scales, they're perfectly balanced, as all things should be. Does anybody have any questions about that? How are we doing first time? So I think that would be a good place to wrap things up for today. Just a reminder, we've got the workshops tomorrow afternoon. So we're going to have the questions to work through then, and a challenge question. Please do come down and ask if there's anything you want to ask about the lecture. Otherwise, I'll see you all in the workshops tomorrow. So see you then.